ओके, सो न्यूक्लियर पावर स्टेशन के बारे में आपको क्या पता है? क्या कोई बता सकता है जस्ट चैट बॉक्स में? इज इट गुड, इज इट बैड, इज इट वर्स, is it problematic, is it advantageous? PARC is different and Tarapur is different. Okay, it is advantageous. Okay, so now we'll start with the today's session. Okay, so now starting with the today's session, we have first we are going to see the advantages and disadvantages of nuclear power station. न्यूक्लियर पावर स्टेशन में सबसे पहले एडवांटेजेस की अगर हम बात करेंगे, देन वी कैन से दैट कंपेयरिंग इट विद द अदर टाइप्स ऑफ पावर स्टेशन, अगर हम बात करेंगे तो अगर कोल या कोई दूसरे फ्यूल बेस्ड प्लांट की अगर हम बात करते हैं, तो इफ यू सी द वेट टू एनर्जी रेशो, अगर न्यूक्लियर पावर प्लांट की बात करेंगे तो वेट टू जो पावर रेशो है, इट्स वेरी ऑप्टिमल। मतलब ये काफी अच्छा है, क्योंकि 1 ग्राम ऑफ यूरेनियम इज इक्विवेलेंट टू 200 टन्स ऑफ कोल। तो अगर आप 200 टन्स ऑफ कोल को अगर आप बर्न करके जितना एनर्जी आप ले सकते हो, उतना 1 ग्राम ऑफ यूरेनियम को अगर आप क्या कह सकते हैं उसका रिएक्शन करवाते हो तो आपको मिल जाता है। सो दैट्स द ब्यूटी ऑफ दिस पर्टिकुलर न्यूक्लियर पावर स्टेशन। ओके, सो मूविंग अहेड विद दिस, आगे बढ़ते हैं। सेकेंड एडवांटेज जो है हमारा, दैट इज न्यूक्लियर पावर स्टेशन इज बेसिकली रिड्यूसिंग द डिमांड फॉर कोल, ऑयल एंड गैस। सो if we talk about the coal and oil and gas which is used in other power plants, तो अगर कोल से हम समझो 5 मेगावाट इलेक्ट्रिसिटी प्रोड्यूस कर रहे हैं, तो उतने ही अमाउंट ऑफ कोल को हम बचा सकते हैं अगर इफ यू आर यूजिंग द न्यूक्लियर पावर स्टेशन, और वहां पर सिर्फ कुछ ग्राम्स ऑफ यूरेनियम से ये सारी चीजें, इतना सारा अमाउंट ऑफ एनर्जी जनरेट हो सकता है। दैट इज अ फर्स्ट एडवांटेज। Second, we can say that cost of fuel is also reduced if we compare it with the oil, gas and coal, because if you are handling large amount of coal, large amount of oil and large amount of gas on a regular basis, do you think that any power plant is a 24/7 operation? You agree with me? Just type yes in the chat box if you agree with me. राइट, सो थर्मल पावर प्लांट, हाइड्रो पावर प्लांट, जो भी है पावर प्लांट, जनरेशन कैपेसिटी जिसका भी है, वो सारे क्या है 24/7 ऑपरेशन इनका होता है। सो इफ वी आर एबल टू सेव दैट मच अमाउंट ऑफ मटेरियल फ्रॉम ट्रांसपोर्टिंग फ्रॉम वन प्लेस टू अनदर प्लेस, लाइक फ्रॉम द सोर्स टू द पावर स्टेशन, वो ट्रांसपोर्टेशन कॉस्ट बच जाएगा। इट विल ऑल्सो सेव ऑन द स्टोरेज कॉस्ट। ओके, फॉर दैट मच बिग अमाउंट, तो वॉल्यूम ज्यादा होगा उसका विथ कंपेयर टू आपके ये न्यूक्लियर पावर स्टेशन। सेकेंड पॉइंट हम सीखने वाले हैं वो है हमारा चॉइस ऑफ साइट। चॉइस ऑफ साइट मतलब क्या? वी कैनॉट इंस्टॉल अ न्यूक्लियर पावर स्टेशन एट आवर ओन विश। हमें इच्छा हो गई सोमैया कॉलेज के बाजू में न्यूक्लियर पावर स्टेशन इंस्टॉल करना है, तो हम उसे नहीं कर सकते। क्यों नहीं कर सकते? बिकॉज यू नो द रीजन, राइट? बिकॉज it requires a very huge radioactive materials are used, and it is not that safe if we compared with the less amount of land or less amount of area exposed to the people। क्योंकि आप देख सकते हैं कि विद्या विहार या फिर जो एरिया है वहां पर इतना ज्यादा आपका ये नहीं है, क्या बोलते हैं उसको, जो बैरन लैंड होता है या फिर लैंड में जहाँ पे वी डोंट हैव दैट ओपन स्पेस। ओके, तो ये सारी चीजें हैं जिससे आपको पता चलेगा कि ये पर्टिकुलर जो हमारा न्यूक्लियर पावर स्टेशन है वो हम जिधर चाहे उधर नहीं इंस्टॉल कर सकते। उसको इंस्टॉल करने के लिए हमें स्पेशलाइज्ड जगह पे ही हमें उसको क्या करना होगा, इंस्टॉल करना। तो वो क्या क्या उसके क्राइटेरिया है वो भी हम आज सीखने वाले हैं। सो आई होप यू ऑल आर रेडी विद दिस। आफ्टर दैट वी आर गोइंग टू सी द एक्सप्लोरेशन ऑफ system through the schematic diagram. So whatever the working of nuclear power plant, what are the different types of reactors, what is the schematic diagram of nuclear power plant, ये सारी चीजें आज हम सीखने वाले हैं. Now there are different materials and different components of our nuclear power plant like moderator, coolant, reflector, and there are some materials which are involved in it. Now these materials are playing an important role because they have the specialized characteristics, or they have the you can say they have some property of that material is such a way that it will add a value, okay, in the nuclear power station by its working phenomena. Now next point we are going to discuss is that when we are classifying these reactors, okay, nuclear power plant में एक कंपोनेंट होता है उसको बोलते हैं रिएक्टर. वो रिएक्टर के टाइप क्या है, यहाँ पे आपको दिख रहा है BWR, PWR एंड कैंडू. सो BWR stands for boiling water reactor, PWR stands for pressurized water reactor, and CANDU is for Canadian deuterium and uranium type of reactor. तो ये सारे जो टाइप्स है रिएक्टर के, उनके वर्किंग प्रिंसिपल के बारे में हमको सीखना है. ओके, यहाँ तक सबको क्लियर हो गया? जस्ट टाइप यस इन द chat box. Now when we talk about any power station, you must have seen that in a thermal power plant also you have there is a coal which is burning, and after the coal is being burned there is a formation of ash, right? So ash is then we need to dispose of, right? So like we need to dispose the ash, we need some mechanism by which we can dispose the solid, liquid and gaseous radioactive nuclear waste. तो nuclear waste जो भी होता है उसे हमें क्या करना है? We need to dispose it off, and for that purpose we required a specialized mechanism. Otherwise, though that material is not useful for generating electricity, but that material will be harmful for our you can say people, animal, then your environment, then animals, environment, trees, basically ecosystem, water system. ओके, तो ये सारी चीजें जो है वो आपके न्यूक्लियर वेस्ट की वजह से अफेक्ट हो सकती है. ओके, आई होप यहाँ तक सबको क्लियर है कि हमें ये चैप्टर में क्या सीखना है. तो अभी हम देखते हैं एक एनिमेशन वीडियो जिसमें हमें पता चलेगा कि न्यूक्लियर पावर स्टेशन का एनर्जी जो है वो किस तरह से काम करता है. ओके, आर यू ऑल रेडी?
3 reasons why we should stop you. 3 reasons why we should continue using nuclear.
If it is audible, just let me know in the chat box. Okay.
In this video, we're going to learn about the nuclear reactor. Nuclear reactors are the modern-day devices extensively used for power generation, as the traditional fossil fuels, like coal, are at the breach of extinction. A nuclear reactor is the source of intense heat, which is in turn used for generation of power in nuclear power stations. Its mechanism is similar to that of a furnace in a steam generator. The steam is used to drive the turbines of the electric generator system. A nuclear reactor consists of 3 crucial components: fuel elements, moderator, and control rods. Fuel elements come usually in the shape of thin rods of about 1 centimeter in diameter and contain fissionable nuclei like uranium-235 or uranium-238. These rods vary in number according to the size of the reactor. In large power reactors, thousands of fuel elements are placed close to each other. This region where these fuel elements are placed is called the reactor core. These fuel elements are normally immersed in water, which acts as a moderator. The objective of a moderator is to slow down the energy neutrons in a nuclear reactor, which are produced during the nuclear fission process by the fuel elements. Thermal neutrons, which are the neutrons with energy of about 0.04 electron volts, are capable of producing fission reaction with uranium-235. During the fission reaction process, new neutrons are given out, which have energies of about 1 MeV. This is 1 mega electron volts. These neutrons typically escape from participating in another fission process as they are accompanied by enormous energy release. In fact, the probability of these neutrons produce another fission reaction is 500 times less than that compared to a thermal neutron. This is where a moderator is extremely useful. Moderators have the capability to slow down, or in other words, moderate, the speeds of these high energy neutrons so that they can in turn be used for a chain reaction to trigger multiple fission reactions of other uranium-235 nuclei. Commonly, ordinary or heavy water is used as a moderator in nuclear reactors because of the deuterons present in them, which are capable of slowing down the neutron's speed. Water molecules in the moderator are useful in slowing down the high-energy neutrons, which leave the fuel element after nuclear fission. These high-energy neutrons collide with water molecules, thereby losing out on some energy with every collision and therefore slowing down substantially. A new fission reaction can now be triggered using this slow neutron by striking it with a fuel element. The third and most prominent part of a nuclear reactor are the control rods. In order to get a steady output of energy from the nuclear reactor, every single fission reaction should trigger another fission reaction and ensure the availability of spare neutrons released to trigger the chain reaction. By controlling the number of spare neutrons available at any given time, the rate of nuclear fission chain reactions can be controlled. This control on the fission reaction can be maintained using control rods. The main function of the control rods is to absorb any excess or spare neutron in the moderator in order to prevent any further fission reaction. Usually, such control rods are made of boron or cadmium. To increase the rate of fission reactions, these rods can be removed from the moderator. A steady output of energy can thus be maintained by inserting or removing the control rods in the nuclear reactor. Now that we know the components of a nuclear reactor, let's understand the working of a nuclear reactor. It's usually enclosed in a shield made of thick concrete walls. It consists of a reactor core, pump, and heat exchanger. The reactor core and pump are placed in contact with the water, which is usually the heat exchanger in these reactors. Due to the enormous amount of heat released during the fusion reaction, the surrounding water gets heated up and changes to steam, which is in turn used to turn the turbines. So huge heat energy gets converted into electrical energy. Water is continuously flown in and out of the nuclear reactor using the pump. So a nuclear reactor successfully generates nuclear energy from fission reactions.
Okay, so now you have come to know about what are the different structures, what are the different components in the nuclear power station. Okay, so we will see how exactly this nuclear power station is working, and then we are going with the step-by-step points related in our syllabus.
Have you ever been in an argument about nuclear power? We have, and we found it frustrating and confusing. So let's try and get to grips with this topic. It all started in the 1940s. After the shock and horror of the war and the use of the atomic bomb, nuclear energy promised to be a peaceful spin-off of the new technology, helping the world get back on its feet. Everyone's imagination was running wild. Would electricity become free? Could nuclear power help settle the Antarctic? Would there be nuclear-powered cars, planes, or houses? It seemed that this was just a few years of hard work away. One thing was certain, the future was atomic. Just a few years later, there was a sort of atomic age hangover. As it turned out, nuclear power was very complicated and very expensive. Turning physics into engineering was easy on paper, but hard in real life. Also, private companies thought that nuclear power was much too risky as an investment. Most of them would much rather stick with gas, coal, and oil. But there were many people who didn't just want to abandon the promise of the atomic age, an exciting new technology, the prospect of enormously cheap electricity, the prospect of being independent of oil and gas imports, and in some cases, a secret desire to possess atomic weapons provided a strong motivation to keep going. Nuclear power's finest hour finally came in the early 1970s when war in the Middle East caused oil prices to skyrocket worldwide. Now, commercial interest and investment picked up at a dazzling pace. More than half of all the nuclear reactors in the world were built between 1970 and 1985. But which type of reactor to build, given how many different types there were to choose from? A surprising underdog candidate won the day, the light water reactor. It wasn't very innovative, and it wasn't too popular with scientists, but it had some decisive advantages. It was there, it worked, and it wasn't terribly expensive. So, what does a light water reactor do? Well, the basic principle is shockingly simple. It heats up water using an artificial chain reaction. Nuclear fission releases several million times more energy than any chemical reaction could. Really heavy elements on the brink of stability, like uranium-235, get bombarded with neutrons. The neutron is absorbed, but the result is unstable. Most of the time, it immediately splits into fast-moving lighter elements, some additional free neutrons, and energy in the form of radiation. The radiation heats the surrounding water, while the neutrons repeat the process with other atoms, releasing more neutrons and radiation in a closely controlled chain reaction. Very different from the fast, destructive runaway reaction in an atomic bomb. In our light water reactor, a moderator is needed to control the neutron's energy. Simple, ordinary water does the job, which is very practical since water is used to drive the turbines anyway. The light water reactor became prevalent because it's simple and cheap. However, it's neither the safest, most efficient, nor technically elegant nuclear reactor. The renewed nuclear hype lasted barely a decade though. In 1979, the 3 Mile Island nuclear plant in Pennsylvania barely escaped a catastrophe when its core melted. In 1986, the Chernobyl catastrophe directly threatened Central Europe with a radioactive cloud, and in 2011, the drawn-out Fukushima disaster sparked new discussions and concerns. While in the 1980s, 218 new nuclear power reactors went live, their number and nuclear's global share of electricity production has stagnated since the end of the 80s. So what's the situation today? Today, nuclear energy meets around 10% of the world's energy demand. There are about 439 nuclear reactors in 31 countries. About 70 new reactors are under construction in 2015, most of them in countries which are growing quickly. All in all, 160 new reactors are planned worldwide. Most nuclear reactors were built more than 25 years ago with pretty old technology. More than 80% are various types of light water reactor. Today, many countries are faced with a choice: the expensive replacement of the aging reactors, possibly with more efficient but less tested models, or a move away from nuclear power towards newer or older technology with different cost and environmental impacts. So, should we use nuclear energy? The pros using nuclear energy. 1. Nuclear weapons proliferation. Nuclear technology made a violent entrance onto the world stage. Just 1 year after the world's first ever nuclear test explosion in 1944, 2 large cities were destroyed by just 2 single bombs. After that, reactor technology slowly evolved as a means of generating electricity, but it's always been intimately connected with nuclear weapons technology. It's nearly impossible to develop nuclear weapons without access to reactor technology. In fact, the Nuclear Non-Proliferation Treaty serves the purpose of spreading nuclear reactor technology without spreading nuclear weapons with limited success. In 40 years, 5 countries have developed their own weapons with the help of reactor technology. The fact of the matter is that it can be very hard to distinguish a covert nuclear weapons program from the peaceful use of nuclear energy. In the 1970s, the big nuclear powers were happily selling peaceful technology to smaller countries, which then developed weapons of their own. The road to deadly nuclear weapons is always paved with peaceful reactors. 2. Nuclear waste and pollution. Spent nuclear fuel is not only radioactive, but also contains extremely poisonous chemical elements like plutonium. It loses its harmfulness only slowly over several tens of thousands of years. And there is also a process called reprocessing, which means the extraction of plutonium from spent nuclear fuel. It can be used for two purposes: to build nuclear weapons or to use it as new fuel. But hardly any of it is used as fuel because we don't have the right kind of reactors for that. A milligram will kill you, a few kilograms make an atomic bomb, and even an inconspicuous country like Germany literally has tons of the stuff just lying around because reprocessing sounded like a good idea decades ago. And where will all the waste go? After dumping it into the ocean was forbidden, we've tried to bury it, but we can't find a place where it will definitely stay secure for tens of thousands of years. Over 30 countries operate nearly 400 reactors, managing several hundred thousands of tons of nuclear waste, and only one is currently serious about opening a permanent civilian waste storage: tiny Finland. 3. Accidents and disasters. Over 60 years of nuclear power usage, there have been 7 major accidents in reactors or facilities dealing with nuclear waste. 3 of those were mostly contained, but 4 of them released significant amounts of radioactivity into the environment. In 1957, 1987 and 2011, large areas of land in Russia, Ukraine and Japan were rendered unfit for human habitation for decades to come. The number of deaths is highly disputed, but probably lies in the thousands. These disasters happened with nuclear reactors of very different types in very different countries and several decades apart. Looking at the numbers, we may as well ask ourselves, are 10% of the world's energy supply worth a devastating disaster every 30 years? Would 30% be worth another Fukushima or Chernobyl somewhere on Earth every 10 years? What area would have to be contaminated so we say no more? Where is the line? So, should we use nuclear energy? The risks may outweigh the benefits, and maybe we should stop looking into this direction and drop this technology for good. If you want to hear the other side of the argument, or a short introduction to nuclear energy, click here. 3 reasons why we should continue using nuclear energy. 1. Nuclear energy saves lives. In 2013, a study conducted by NASA found that nuclear energy has prevented around 1.8 million deaths. Even if you include the death tolls from Chernobyl and Fukushima, nuclear energy ranks last in death per energy units produced. While nuclear waste is really toxic, it's usually stored somewhere.
ये जो अभी बताया ना, ये बहुत ही अलग तरीके से क्या बोलते हैं एक्सप्लेन किया हुआ डेटा है। ये क्या बोलते हैं, डेथ पर एनर्जी यूनिट जनरेटेड पर ईयर। से फॉर एग्जांपल, अगर कोल बेस्ड कोई प्लांट है जिसको पीट प्लांट बोलते हैं, वहां पर कोल प्रोडक्शन से लेकर कोल बर्न होके एनर्जी प्रोड्यूस होने तक जो जो एक्टिविटी होते हैं उसमें जितने डेथ होते हैं उनको यहाँ पे कैलकुलेट किया है। बायोमास का अगर हम बात करेंगे तो बायोमास को प्रोड्यूस होते वक्त क्या क्या डेथ हो रहे हैं, एक्सीडेंट्स हो रहे हैं, उसकी बात कर रहे हैं। एंड नेचुरल गैस का एक्सप्लोरेशन से लेके एक्चुअल यूज तक क्या क्या हो सकता है, वो सारी चीजें यहाँ पे कंसिडर किया है। और अगर न्यूक्लियर पावर स्टेशन की बात करेंगे तो उसमें इतना सेफ्टी हमें लेना होता है, और उसकी वजह से बिकॉज इफ यू आर फॉलोइंग द सेफ्टी यू विल डेफिनेटली गोइंग टू सेव द लाइफ्स। ओके, तो इसकी वजह से न्यूक्लियर को हम सेफ बोल रहे हैं, क्योंकि इसमें जो लाइफ या डेथ हो रहे हैं पर ईयर वो सबसे कम है। ओके, आगे बढ़ते, ये थोड़ा अलग पॉइंट है, इसलिए मैंने थोड़ा रुका के आपको एक्सप्लेन किया है।
Death per energy units produced. While nuclear waste is really toxic, it's usually stored somewhere, while the toxic byproducts of fossil fuels are pumped into the air we breathe every day. So, just by reducing the amount of fossil fuels burned, countless cases of cancer or lung disease and accidents in coal mines have been avoided. If we can choose between lots of dangerous stuff being put into a deep hole and lots and lots and lots of dangerous stuff being pumped into the atmosphere, the former seems more logical. Nuclear energy feels way more dangerous though. Single catastrophic events burn into our memory, while coal and oil kill silently. It's like the death rate of flying versus driving. Even in the best case scenario, it would take at least 40 years to switch to 100% renewable energy. So for as long as we continue using fossil fuels, nuclear energy will save way more lives than it destroys. 2. Nuclear energy reduces CO2 emissions. Nuclear energy is arguably way less harmful to the environment in terms of climate change than fossil fuels, our main source of energy. Since 1976, about 64 gigatons of greenhouse gas emissions have not been pumped out thanks to nuclear energy. And by the mid-21st century, that could amount to an additional 80 to 240 gigatons. Humanity's energy consumption is rising steadily. According to US government projections, China alone will add the equivalent of a new 600 megawatt coal plant every 10 days for the next 10 years. China already burns 4 billion tons of coal each year. Coal is cheap, relatively abundant, and easy to get to, so it's not likely that humanity will stop using it soon. Nuclear energy might be the only way of dampening the effects of climate change and preventing a catastrophic man-made global warming. Compared to the other things we do, nuclear energy is relatively clean. So even if it is a good idea to quit nuclear energy long-term, it might be a good solution for the next 100 years or so compared to the alternatives. 3. New technologies. Maybe technology will solve the problem of nuclear waste and dangerous power plants. The nuclear reactors we've used so far are mostly outdated technology because nuclear innovation stopped in the 1970s. There are models like the thorium reactor that could solve the problem altogether. Thorium is abundant, really hard to turn into nuclear weapons, and up to 2 orders of magnitude less wasteful than current nuclear reactors. The waste material might also be only dangerous for a few hundred years, in contrast to a couple of thousand years. 1 ton of thorium is estimated to provide the same amount of energy as 200 tons of uranium or 3.5 million tons of coal. So while we cannot know for sure if alternative nuclear technology will keep its promises, shouldn't we at least do more research before we forego an opportunity to solve lots of humanity's current problems? It might not be an easy challenge, but that hasn't stopped us before. So, should we use nuclear energy? There are risks involved in any great human endeavor, and we have to make an informed decision rather than rely on gut feeling. If you want to hear the other side of the argument, or a short introduction to
Okay, so now you are seeing the animation, visuals, and you come to know about the various interesting topic about the nuclear power station. Okay, so now keep yourself ready with a paper and pen. So we are starting with our theory part. Okay, so first point we are going to see, that is the advantages of nuclear power station. Okay, so I am visible to you, right? Perfect, and I will be sharing a screen also. Give me a moment. Perfect. So first point we are going to see is the advantages and disadvantages. Screen sharing shuru hua? Okay. So first advantage you write down that it reduces the demand for coal, oil and gas, so that it is saving the considerable cost of fuel. That is the one thing we can say about the advantages. Second is the station capacity is negligible because the fuel amount which is required is very small. If the volume of the fuel is very small, you can say that there is a less cost. Okay, less cost of transportation, less cost of you can say that material also. And then only thing is that we need to ensure the safety of that material which is we are going to use as a fuel. Okay, then the area and amount, or we can say that the volume which we required for a nuclear power station is very less if we compare it with the other conventional plant. अगर hydro power plant की बात करेंगे तो hydro power station के लिए we required a space for a dam, and then we required a space for the penstock and the reservoir, like that, and after that you need again the space for the actual plant. तो nuclear power station में ऐसा नहीं होता है. Nuclear power station में you are having say for example you are having say 1000 megawatt of capacity, then the area which is required for that plant and the volume of the space which is required is very less. Okay, second thing I would like to say that, or we can say that, or you can just write it down, that this nuclear power station is partially independent of other location criteria. Say for example, hydropower station के लिए we required a dam, thermal power station के लिए we required a you can say coal mines. Okay, so for nuclear power station we don't require any kind of such criterias. What we require is just a water supply. So if water supply is available, you can say that we can get a good amount of electricity from the plant. Okay, next is that if we get a good amount of water, because water is required for the cooling purpose, so if there is a good cooling available, we can get a safety of a plant, as well as we will get the you can say we can get that opportunity to bring the plant to near to the load center. Okay, so if the plant is installed at the load center, your transmission cost is reduce. Okay, now we can say if we are comparing is running charges, तो जैसे हमें पहले कोल जो है वो से 200 टन लगता था, अभी हमें सिर्फ 1 ग्राम ऑफ यूरेनियम फ्यूल इज रिक्वायर्ड. सो हमारी जो कॉस्ट है, रनिंग कॉस्ट जो है फ्यूल की, वो कम हो जाएगी, क्योंकि ये 1 ग्राम जो आपका फ्यूल है वो कई महीने चलेगा या कई दिनों तक चलेगा एज पर इट्स कैपेसिटी. And we can say that over a long run the running cost of this plant is very low. So next point, you can say that very low running charges, then it is very economical and it will generate the bulk electrical power. Okay, तो ये सारे एडवांटेजेस है आपके न्यूक्लियर पावर स्टेशन के. अभी एडवांटेजेस में कोई छूटा है पॉइंट ऐसा लगता है आपको, तो चैट बॉक्स में मुझे बताओ, या जो हमने पॉइंट्स अभी डिस्कस किया वो मुझे चैट बॉक्स में बताओ. What are the advantages of nuclear power station? आपने लिखे होंगे ना? You got the question? Yes. Bulk power making, low running charges. Yes. What else? Low fuel cost, less amount of fuel. Yes. ओके, परफेक्ट. सो ये सारे पॉइंट्स आपके नोटबुक में आपको लिखना है. जिन्होंने नहीं लिखे हैं वो यहाँ से रेफर कर सकते हैं. परफेक्ट, परफेक्ट. नाउ गोइंग टू द डिसएडवांटेजेस. If you talk about the disadvantages, the very first disadvantage you can say, as it is a raw material, is radioactive material. It means its disposal is very problematic. But before disposal, you can say that exploration of that material, storage of that material, and refining of the radioactive material is again a challenge. Okay, so we need to require a very good efficient manpower, as well as we required a very high technology. Okay, so that technology will help you to create a proper flow of energy from the uranium atoms and the radioactive chain reaction, and then installation of different barriers and different kind of structures for preventing a contamination. Preventing the contamination is again very important. Okay, so high technology is required for the erection and commissioning of a nuclear power station. ये एक प्रकार से आप बोल सकते हो कि हमारे न्यूक्लियर पावर स्टेशन का ये एक डिसएडवांटेज है. ओके, ऑल्सो वी कैन से दैट द कैपिटल कॉस्ट विच इज रिक्वायर्ड एट द स्टार्टिंग और एट द इनिशियल स्टेजेस इज वेरी हाई. तो अगर आपको कोई हाइड्रो पावर स्टेशन इंस्टॉल करना है, देन यू नीड टू कंस्ट्रक्ट अ डैम, or you can use a ready-made dam which is available. But if you want to install a nuclear power station, then you require to install a large amount of money or capital into it, so that its mechanism, its structure, its technology can be well paid off. Okay, आगे बढ़ते हैं. The fuel which is used is very costly in comparing with its weight, and the radioactive and difficult to recover. So if we are using the fuel which is hardly having any difficulties of exploration, तो ये डेफिनेटली हमें जमीन से निकालना होगा. इसके रिजर्व्स रहेंगे, वहां से हमें इसको माइनिंग करके निकालना होगा, उसको रिफाइन करना होगा, और ये सब एक्टिविटी जब करेंगे तभी उसमें किसी को ये रेडियो एक्टिविटी का नुकसान नहीं होना चाहिए. ओके, एंड फॉर दैट पर्पज यू कैन से this type of unit is very much in difficulty. So cost is very, again, a very important point to understand. Second is that waste product of fission process. इसमें फिजन प्रोसेस होता है, कैसे होता है वो हम देखेंगे. उसका कुछ एनिमेशन पार्ट हमने देखा है, राइट. सो if we are using this material as a fuel, then the इसका जो डिस्पोजल है, डिस्पोजल ऑफ वेस्ट, दैट विल बी अगेन अ प्रॉब्लम फॉर अस. ओके, सो ये काफी इंपॉर्टेंट डिसएडवांटेजेस है. देन वी कैन से दैट दे आर नॉट सुटेबल फॉर द वेरिएबल लोड. नाउ हाउ वी कैन से दैट? नाउ व्हाट डू यू मीन बाय वेरिएबल लोड एंड व्हाट डू यू मीन बाय कांस्टेंट लोड? वेरिएबल लोड मतलब ये पावर प्लांट आपके डेली चेंजेस जो लोड हो रहा है उसको सेटिस्फाई करता है. ओके, एंड नॉन वेरिएबल लोड या कांस्टेंट लोड जिसको बोलते हैं, वो है कि इतने अमाउंट ऑफ पावर वो हमेशा प्रोड्यूस करेगा और हमेशा उसका कंजम्पशन होना चाहिए थ्रू आउट द ग्रिड. ग्रिड मतलब आपका इलेक्ट्रिक ग्रिड में कहीं पर भी ये पावर आप कंज्यूम करने के लिए दे सकते हो, प्रोवाइडेड ये पावर जो है ये वेरिएबल नहीं होगा. इट विल बी ऑलवेज कांस्टेंट. दैट इज अ नेक्स्ट डिसएडवांटेज. ओके, सो आई होप यहाँ तक सबको क्लियर हुआ होगा. तो now let me know what are the disadvantages in the chat box. Okay, so now we will see the how to select the site selection criteria किस तरह से होता है हमारे न्यूक्लियर पावर स्टेशन का, ये अभी हम लोग देखते हैं. Okay, so I hope your paper pen is ready. You are taking down the notes and there are some 41 students who are listening right now. Okay, so first selection करने के लिए हमें सबसे पहले साइट में क्या क्या फैसिलिटीज होनी चाहिए वो देखते हैं. यस, डेफिनेटली द पावर स्टेशन शुड बी विस्टैंड ऑन दैट लैंड. मतलब पावर स्टेशन वो लैंड पे अगर इंस्टॉल करेंगे तो उसके सॉइल की कैपेसिटी होनी चाहिए. द लैंड शुड हैव द बेयरिंग कैपेसिटी. बेयरिंग कैपेसिटी मतलब क्या? लोड बेयरिंग कैपेसिटी. ओके, नाउ this particular nuclear power station site is considered as when we are using the nuclear power technology, we required a large amount of water for the cooling purpose, and that cooling purpose as well as for the steam, for conversion of heat energy into the steam energy, we required the nuclear power station site is near to the water. So the water body can be your sea, your river, okay, like that. Next is it should be away from the populated area, because if any accident took place or if any leakage took place, then the populated area should not be affected. Okay, that is the point. Then you can see it should be near to the load center. लोड सेंटर जो है आपके न्यूक्लियर पावर स्टेशन के नजदीक होने चाहिए, ज्यादा भी दूर नहीं होने चाहिए, so that the amount of losses in the power transmission can be reduced. Okay, next is the site should be equipped with the waste disposal. न्यूक्लियर पावर स्टेशन का जो वेस्ट है उससे हमारा साइट जो है वो अवेलेबिलिटी होना चाहिए डिस्पोजल के लिए. It can be a extra area where we can dispose of, or we should have some mechanism by which deep inside the earth crust or in the seashore also there should be some facility to dispose the nuclear waste. Okay, इतना क्लियर हुआ सबको? एंड लास्ट एंड वेरी इंपॉर्टेंट, अगर हम न्यूक्लियर पावर स्टेशन इंस्टॉल कर रहे हैं, इट शुड बी इन द रिस्ट्रिक्टेड एरिया, बट देयर शुड बी अ transportation facility available. Okay, so if we want to install the plant, we require a machinery to be transported, right? So that thing is very important. So it should be near to the transportation facility. So now tell me, what are the different site selection criteria in the chat box? Perfect. So now we have seen the site selection criteria of nuclear power station. Now we are going to see the next point, that is the schematic diagram of nuclear power station. So I will be sharing a nuclear power station diagram with you, so that you can just draw this diagram where most of the part is similar to your steam turbine powered plant. Like you can see here, there is a heat exchanger, and heat exchanger is basically taking the heat from the nuclear reactor and then the water is converted into the steam. Okay, and that steam is impinged on the turbine, steam turbine, and turbine is rotating. Now this rotating turbine is basically generating electricity with the alternator. So turbine is acting as a prime mover. Okay, so moving ahead with this, I will give you some time for drawing this diagram in your notebook. So once you're done with it, just type done in the chat box. Draw it properly, sincerely. I hope it is visible to everyone and you done with the drawing. आप आपके फोन पे भी zoom कर सकते हो मेरे ख्याल से. Is it possible for you to do zoom in on your screen? Okay, so now I hope you have done with the diagram. So now moving ahead with this. In this particular diagram, we are actually seeing the schematic diagram of nuclear power station, which is a very you can say basic thing, because here the diagram is not giving you details of reactor. Okay, so nuclear reactor को हम एक just नाम दे रहे हैं, एक ब्लॉक दे रहे हैं, और उसके अंदर क्या होता है वो हमने एनिमेशन में तो देखा है, बट अभी उसका एक्सप्लेनेशन देखते हैं कि एग्जैक्टली उसके अंदर क्या होता है. सो आई होप यू आर ऑल रेडी एंड यू कैन टेक डाउन द नोट्स as I am speaking and explaining the things to you. Okay, so fusion of this uranium U-235 and thorium is basically producing a large amount of heat in the reactor. Okay, and that heat is basically used in the heat exchanger to convert that water into the steam. Now the nuclear reactor is an apparatus. You can say that it is an apparatus in which the fission of above radioactive element is carried out as per the flow which we want. So if we are just putting the nuclear fuel in the reactor, it is not going to happen, the reaction. So we need to use the control rod, we need to use the moderator, we need to use the free neutrons. Okay, and because of this chain reaction, we also have so many sensors. Now that's the beauty of this particular nuclear power station, is that the nuclear power station has tremendous amount of sensors and the automation system which is used for the safety of a people who are working inside the plant as well as people who are living nearby. Okay, तो ये बहुत important point है. After that, this nuclear reactor is like a pressure vessel, because whenever there is a heat generated, the heat generation is then utilized, and that generated heat is basically leading to the expansion of the air or expansion of gaseous and liquid material which is nearby. And because of that expansion, there is a limited volume which is causing the pressure rise, and this pressurized material is inside this nuclear reactor, and this is a one kind of pressure vessel. The pressure vessel is also considered as the material inside the pressure vessel is not allowed to go outside. Okay, it is not allowed to go outside, and hence you can see that there is a this particular reactor is the pressure vessel is containing this fuel rods, moderator, and you can say control rods. Okay, so now if we talk about the moderator, now what is the use of moderator, that we are going to see. Moderator का मतलब ये है कि whenever there are large number of neutrons which are coming out of the chain reaction and the reaction is becoming uncontrollable, that time if the material is absorbing the excess neutrons, then the speed of that reaction can be controlled. Okay, so graphite, heavy water, or beryllium are these names of the materials which are work as a absorption of neutrons to slow down the reaction within the fraction of second, and hence the moderator should have the some qualities to perform the activity better, and that you can say that it should be light in weight. You can write down this point about the moderator. It should be light in weight, it should slow down the neutrons, and it should not that way absorb the neutrons so that the chain reaction will stop by all. It just need to slow the speed of the neutron, and it should also have the high melting point because they are in associated with the fuel rod. तो फ्यूल रॉड के आजू बाजू में ही अगर वो है तो उनका मेल्टिंग पॉइंट जो है दैट इज वेरी हाई. नाउ if you talk about the chemical reaction, chemical stability should be very much high, and the different type of oxidation या oxide material are there, oxygen is there, and the oxidation is near, you can say that corrosion kind of thing is happening, so that material should be highly resistive to the corrosion. Okay, so this is how you can say that moderator is playing a important role. Now also we looking for the control rods. Okay, control rods are like whenever we need to stop the fuel flame, what we are doing, अगर हमने thermal power, hello, am I audible to you? Hello. Okay, so there is some network glitch at my area. Okay, so now the point was we are discussing is control rods. Okay, so control rods are used to stop the reaction, and it is having a very high capacity to absorb the neutrons. Okay, so we'll see one video now how the Tarapur nuclear power station is working, and let's explore the things.
Nuclear plant. It's a place very few people have access to. And for the first time, a camera crew will cross the lines of its forbidden boundaries to enter an exclusive territory. To get a glimpse of a world rarely seen.
So this is as close to the actual reactor that you can possibly get.
This is an insight to what goes on behind the walls of a nuclear power reactor.
What you're carrying is 1 million units of electricity.
1 million?
An insight into the complexities of how things work.
This is probably the most futuristic thing I've seen outside of science fiction films.
This is Tarapur Nuclear Power Plant, unlocking power.
This is my chance of a lifetime. I'm inside one of India's most secure installations with a 24-hour pass to explore its most historic nuclear plant. I've already been through some strict security, and now I'm finally ready to enter the fascinating world of nuclear power. So what happens inside a nuclear power plant? Mostly because people don't really know what goes on inside the walls, they tend to give in to their imagination. But what is actually happening inside these walls is that a clean source of energy is being used to produce electricity.
Inside Tarapur Atomic Power Plant, nuclear energy production is in full swing. Tarapur Units 3 and 4 are India's most up-to-date pressurized heavy water reactors in operation, and each is capable of generating 540 megawatt of power.
Worldwide, there are 31 countries that have about 430 commercial nuclear reactors. India has 21 nuclear reactors that are operational, which are run by the Nuclear Power Corporation of India Limited, or the NPCIL.
Tarapur is India's most iconic nuclear plant. When the first two nuclear reactors came up in Tarapur way back in 1969, it was an historic event. It was a long journey for the nuclear equipment, which were transported all the way from foreign shores. An agreement had been signed in 1964 between General Electric USA and India to set up the plant. Two more units, Tarapur 3 and 4, came up by 2005-2006 using indigenous technology. Put all four together and you have the largest nuclear power plant in the country in terms of capacity.
We have got 4 units. The oldest unit number 1 and 2, they are generating 320 megawatt per day. It comes out to be 7.6 million unit per day. And in Tarapur 3 and 4, this is the latest unit. They are generating around 26 million unit per day. And that is very big amount of electricity. I can say the TNS site is giving 1/3 generation of the total whatever NPCL is producing as of today.
And at the heart of nuclear power generation is that colossal dome-shaped structure around which the entire plant is built, the nuclear reactor.
The nuclear reactor is where all the action lies. It is here that the electricity is generated. But before we actually cross into that exclusive zone, let's get down to how nuclear electricity is. While nuclear energy is produced in the reactor, everything is controlled in what is perhaps the most important room in the plant, the control room. The control room is the hub of a live 24-hour production of nuclear power and is manned by personnel working around the clock.
I'm inside the nerve center of the nuclear plant, the control room. This is where every minute detail of the nuclear plant is monitored with extreme precision. These are probably the most fascinating screens in the control room. This is the very heart of the nuclear reactor. Basically, what these screens are monitoring is the amount of energy generated by the reactor and the amount of energy extracted. It's critical to get the balance right.
These numerous parameters are meant for the safe operation of the plant. If anything at all were to go wrong, the reactor would lose 0.5% of its power per second, and in about 3.5 minutes, the entire system would shut down. The highly skilled and trained personnel in this control room keep a hawk's eye on all monitors and are responsible for making sure that the parameters are under control.
I take care more than 20,000 plus parameters of the plant. It should be within its limits so that every time I have to be vigilant and take care of those parameters. After all, people's safety is in our hand only.
So the man in control of the control room is the shift charge engineer. Mrs. Rahul, tell me, what is the most challenging part of your job?
Most challenging part of the job is mainly we have to operate this plant safely and at a authorized power level. That is, I think, it is the most challenging part.
And how advanced is your system now?
This plant control is very much advanced, and we are monitoring and controlling all the system parameters inside this control room. All these control parameters, this can only be monitored inside this control room. So in that way, it is this plant is safe.
It's very secure. So what it means is that this system cannot be interfered with from the outside, and it cannot be hacked into, basically. This control room has a special monitor installed which keeps track of seismic activity in the area. In the event of an earthquake, the power plant will trip and automatically shut down.
Every day, along with power generation, refueling of the machine is also done, which is a critical part of Tarapur's daily operation.
The refueling in the pressurized heavy water reactors is carried out every day when the reactor is operating. So the operations has to be carried out totally remotely from the control room, and these operations are monitored by two independent computers of both sides fueling machines, which has to work in synchronism as per the programs which are written, and adequate safety provisions are given in this system to carry out such a refueling in an orderly manner and safe manner.
Since refueling happens at the core of the nuclear reactor, robotic machines that function as arms push the new fuel bundles into the slots in the calandria so that they can undergo nuclear fission. And on the opposite side, a similar robotic arm takes out the spent fuel bundle.
So currently it's refueling time. Let's find out about the process here. Hi. Could you tell us about the refueling process? How often do you do it?
Total we have 392 channels. Out of these 392 channels, per day we carry out refueling of 2 to 3 channels. Refueling of these 2 to 3 channels, we have two machines, one on north side of the calandria, another on the south side of the calandria. We take out these machines from their park position to the channel position. We align these machines to the channel with our high precision sensor. After aligning, we clamp this machine on the channel. We open up the boundary of the channel. We push new fuel bundle from the one side. Suppose I am starting my refueling from the north side, so I'll push new fuel bundles from the north side, and I'll extract the spent fuel bundle from the south side of the machine. This way we complete our refueling.
And all that is monitored from here?
All the parameters are remotely monitored here, and this whole operation is carried out using a microcomputer. So in totally automatic mode, this refueling is being done. All the feedbacks are available on this panel, both way, in this computer also and in these indications also. All the feedbacks are available to the panel operator.
And I'm soon about to witness what very few people in the world ever will: nuclear fuel being loaded into the reactor.
Other than maintenance engineers. And as you can see, we need to wear protective clothing for that.
The protective clothing and gear is meant to be a barrier against radiation contamination. Since this is a highly radioactive zone, the radiation levels need to be monitored carefully.
You can't mention the word nuclear power without the word radiation following it. Now, we've all used this word often enough, but without completely understanding what it actually means. So what does radiation exactly mean?
The universe is made up of particles. Some particles release excess energy. This excess energy released in the form of electromagnetic waves is called radiation.
We live in a radioactive world. We are exposed to radiation from the sun, from outer space, from the earth, or even the food and drink we consume. In fact, you may be exposed to more radiation eating a banana, taking an X-ray, or a round trip to New York than you would if you lived an entire year near a nuclear power plant.
Tarapur has different zones numbered from 1 to 4 based on the radiological probability of each zone. Zone 1 is the least radioactive area, while Zone 4 is a highly radioactive area with a higher contamination potential. Workers and equipment are thoroughly checked for contamination when moving from a higher contamination area to a lower one, so that it minimizes the chance of radioactive particles being transferred. The time was drawing near to what would be an ultimate experience for me. A rare chance that extremely few people in the world get to experience. A chance to enter the reactor building.
Now we will be entering the reactor building 3. So it's what we are seeing over here is the main airlock. There will be two doors. These are automatic doors, and this is the outer containment door, and then there will be one more inner containment door. So before entering, we will put on this protective gear, the gloves and the shoes. Inside right now, our fueling operations are going to start. So I think we will be able to get a view of that also.
There's another door.
Yeah, there's another door. Actually, there are two different containments in this. The whole reactor building is having two containments, the inner containment and the outer containment. And both these two, when there's a differential pressure between here, inside the other door and outside, they are meant to prevent any release of radioactivity to the outside environment. The two separate set of buildings. One is completely enclosing the other one. So we will just move now to the inner one.
Oh my God. So this is as close to the actual reactor that you can possibly get.
I was about to witness up close what very few people in the world have seen. The actual loading of a fuel bundle just before it is inserted into the reactor for nuclear fission to take place. These new fuel bundles have gone through some stringent quality checks before they arrive here. The raw fuel bundles, which are made in the nuclear fuel complex in Hyderabad, the center which makes all nuclear fuel, are carefully brought to the plant and thoroughly checked for their quality.
After receiving fuel bundles from the manufacturer unit, we are doing the three tests. One is a physical test, then it is a dimensional test, and third is a integrity test. After doing the visual and the dimensional checks, we are putting three bundles in one bumming chambers in individuals. And after covering it, we are pressurizing this by the helium gas up to 6 kg for 1 hour.
The helium test is used to detect leaks. Once the new fuel bundle passes it, it is good enough to be loaded into the calandria.
Now we are inside this new fuel loading area. It's also one of the critical areas, and from here we will load the fuel manually, and then we will go ahead. This fuel goes after that, it's all through a system driven.
Is it safe for me to handle it?
Yeah, the new fuel is not, there's no problem in that, and it's visitor friendly, so there's no problem. So I will just lift one of these bundles. It's a bit heavy, and we just have to put it here. The fuel goes in pairs. So would you like to load the other one?
Sure, why not?
Now what you are carrying is 1 million units of electricity. This one fuel bundle.
1 million?
1 million units of electricity.
It's heavy.
I think you are able to lift it quite comfortably.
It's not that easy.
Now here onwards the hydraulic ram will advance, and then the fuel goes into this new fuel maxim, and then again the transfer system, the fueling machine, which we'll be seeing next.
All right.
So but now we have loaded together, both of us have loaded 2 million units.
2 million units. Let there be light.
Now this is the vault where all the coolant channels are there, in which the uranium fuel is there. So this area is inaccessible, and it is closed by this door, which has got an interlock. It won't open when the reactor is above a particular power, 0.1% power.
Above 1% power.
0.1% power, we can't open it.
So this is one of the two entry points into the vault of the nuclear reactor. You can enter only once the plant is shut down for maintenance.
Inside the radiation fields are significantly high. So outside it's pretty safe. There's no problem over here. So we'll just see from there the wing window. The other side of it we can see inside. This is called the wing window. And from this wing window you can just go inside and see. You can go near, sir, there's no problem out here. And what you're seeing inside is the fueling machine.
This is probably the most futuristic thing I've seen outside of science fiction films. This is the robotic machine that actually loads the fuel.
Yeah, exactly.
What we just put in there.
Yeah, right. What you have put in here, that is the fresh fuel has come into this machine. It has taken this fuel and now it will be loading into this calandria, or we say the coolant tubes. There are 392 coolant tubes, and each of this machine will just now swing and 90 degree and align with those coolant tubes. Right now he is going to do the first channel of today.
Those things, each one is there basically to maintain a certain temperature. How much what kind of temperature are we talking about?
If you see closely inside, there is a plug outside. We call it the sealing plug or the closure plug. So that inside those tubes there is a temperature of around 300 degrees centigrade and a pressure of around 100 kg per centimeter square. These refueling operations in this plant, we have now taken out the seal plug and put it back around 7,000 times. That means around 14,000 times we have opened it and put it back. So it's pretty safe. And overall, among the Indian nuclear power plants, we have now done this operations for around 70,000 times. So that much expertise we have developed now.
And all this nuclear energy that is generated finally finds its way to the mammoth turbine room.
I'm now heading into the turbine room. That's the place where electricity is actually generated. But before I go in there, I better put on these earmuffs because I've been told it gets really loud in there. All set?
The production of nuclear electricity is done on a massive scale at Tarapur Nuclear Power Plant. The nuclear energy generated is finally transformed into electricity in the turbine room.
Now this feels like a proper nuclear power plant. I can feel the heat being generated from the steam that is being produced inside the turbine. Behind this turbine, there are 2 turbo generators. And over there, on that meter, we can see the actual amount of electricity being generated in megawatts.
Once the electricity is generated, it is transported through a transmission network or grid, which are wires that wheel high voltage power over long distances to the substation. The voltage is then stepped down at the substation and then distributed to the end user at voltages suitable for home use. So where does nuclear power score over other forms of energy?
The nuclear power is location neutral. That means the nuclear power plants can be set up at any of the locations irrespective of the availability of the fuel. Another thing is the nuclear power is a base load generating technologies. That means it generates the electricity 24 hours, all 7 days in a week, or you can say 365 days in a year.
Presently, thermal is acting as a base load station. All our thermal resources like coal and petroleum, they are depleting fast. Well, you see that renewables like our solar and wind power, they are supplying electricity intermittently, so they cannot be considered a base load station.
So when it comes to nuclear power, where does India stand?
India has more than 4 decades of safe nuclear power generation, and we have mastered pressurized heavy water reactor technology. We have comprehensive capabilities in designing, construction and operation, and we have demonstrated our capabilities in par with the world-class standards. In fact, one of our reactors is operated more than 750 days continuous operation, which achieved the second longest duration of operation among the world reactors. This shows our competency in par with the world class.
But getting to be world class doesn't just happen. At Tarapur, complex technology is handled by extremely skilled personnel, and it is not by chance that every single person working at Tarapur has got here after a long, intense period of training.
The nuclear reactor is a very big power generating utility. When you are operating nuclear plant, the enormous responsibility of operating this plant in a safe and efficient manner is very huge. And therefore, we have to make sure that every step, starting from induction to training to continual training and field experience, that whatever pool of manpower which we are utilizing for operating this plant are indeed worth it. So that's why we have a very elaborate qualification and licensing program. These licenses are awarded by the Atomic Energy Regulatory Board. Broadly, we recruit at 3 different levels, namely technician, supervisor, and scientific officers. Those who are shortlisted from written examination undergo interview. If you clear that interview, then you are just inducted into a rigorous training program. Just like breathing is required all the time, similarly, continual training is part and parcel of operating a nuclear power station. We cannot be complacent that, okay, you are licensed, you can continue to operate. If he is a licensed control engineer, he cannot continue to be so unless he clears himself after 3 years. So there is a requalification every 3 years.
This is the place that turns these men into pros. Under simulated conditions, these men face situations, some of which they are improbable to face during their tenure at the plant. But their extensive training here will prepare them for any eventuality in the future, for real. This is an exact working replica of the control room that trainees get to work with.
Basically, we are having normal day-to-day operation in the plant. These are normal operations. Then infrequent operations, those which do not occur normally. And then some are our emergency operations also. And we give training on all those things. This is a infrequent operation where they do not get an opportunity in live system. So we will simulate a sequence and they will act and take actions as needed as per the scenario. Whenever we give an exercise, basically we evaluate them on 9 parameters. So those parameters are also set. Their attentiveness to panel, their initial actions, their subsequent manual actions, their teamwork, and procedure adherence. आज हम एक exercise करेंगे class 4 failure का. And your roles I will just define. You are the assistant chief engineer. You are the overall control of the panels in the station.
So detail to safety and training of personnel is key to running Tarapur successfully. While nuclear power has certain advantages over other sources of power,
people are still wary about nuclear power. In the nuclear world, an accident anywhere is an accident everywhere. And some of these accidents, admittedly, have left their scars on nuclear history. But these very accidents have also provided vital safety lessons for existing nuclear facilities around the world.
In nuclear power technology, we have a good international cooperation. The incidents which happened in the internationally, right from 3 Mile Island accident, Chernobyl accident, and even the recent Fukushima accident, all have been, the internal details have been very well shared among the international community. The experiences gained and the inadequacies, everything has been well analyzed. And in Indian context also, we have taken several measures to strengthen the safety features. We have provided additional features in the new reactors as well as in the existing reactors based on these accidents.
So how safe is this nuclear plant? Tarapur functions on a defense-in-depth philosophy, which essentially means that there are multiple barriers in place to prevent disasters. It starts with the uranium, which is in ceramic pellet form. These are encased in sealed zirconium alloy tubes to form fuel rods, which in turn are confined within a steel pressure vessel. Finally, this is enclosed in a containment structure with walls nearly 2 meters thick.
If we see the onion, before reaching to the core, there are multi-layers. Similar philosophy is applicable for nuclear power plants. Basically, it is multi-layer prevention including the physical barrier to prevent the release of the radioactivity to the environment. The basic aim of the defense in tech philosophy to prevent the accident. Suppose accident do happen, then we have to limit the consequences and subsequently prevent the progression of the consequences to the environment.
The plant has got a two-group safety concept. With each group of safety independently can cater the various basic safety functions of the nuclear reactor, what we call it 3 C's, that is control of reactivity, core cooling and containment. So each group is capable of performing all these 3 functions. In order to achieve that, the plant layout has been made in such a fashion that half of the safety systems are physically located in an independent structure and half are located in other part of the area of the plant.
The walls of this dome are fortified to ensure that no radioactivity escapes from the inside. Apart from its thickness, there is a second layer of wall with negative pressure between the 2 walls so that in case of a leak, the pressure from the outside prevents the inside radioactive air from leaking out.
We have got these 2 barriers, inner wall and outer wall. If activities, let us say it goes out, then we have got a 1.6 kilometer exclusion zone. Beyond that only, people are permitted to habitate.
Even beyond the fringes of the exclusion zone, a strict vigilance is kept on the radiation effect on the environment. The Department of Atomic Energy has kept a watchdog called the Environmental Survey Laboratory that tests the environment for any traces of harmful nuclear radiation.
We started our work right from 1964, much before the plant started operation. And we were doing for last more than 4 decades. We collect samples like air, water, and meal, fish, vegetable, grass, seawater from this local environment. The primary role of the environmental monitoring is to demonstrate that dose to the members of public is within the limit prescribed by regulatory agency of India based on international guidelines. The Tarapur nuclear power station and other facilities are safe and there is no impact to the environment due to their operation.
Perhaps one of the biggest advantages of nuclear power generation is that there is no emission of greenhouse gases and the surroundings are kept green.
And well, this butterfly park is proof enough.
I have been inside the nuclear reactor building where nuclear energy is produced and the turbine room where electricity is generated. But there was still one more area left for me to explore, the spent fuel bay area.
So what happens to used fuel bundles once they're discharged by the nuclear reactor? I guess this is where we find out.
This is our storage bay for TAPS 3. We will see it here.
What is happening here?
So this is our main spent fuel storage pool of TAPS 3, and there is a similar pool of TAPS 4. In this pool, we can store our reactor fuel for a period of 10 full power years.
You're talking about the bigger pool?
Yeah, the bigger pools.
And these ones?
These smaller pools are the receiving bays. When the fuel comes from the channel, the discharge fuel
from the reactor.
It comes in pairs. 2 bundles come here. We take them, receive them over here, and then we push it down to the bigger pool. And then there we keep them in those storage trays. What you are able to see there are the trays.
Yeah.
So we keep them there stored. This water is for cooling as well as for shielding purpose. Since
it's regular water. What kind of water is it?
It's a DM water.
DM.
It's a demineralized water. It's just we are maintaining pure chemistry of the water. It's nothing much special. It's for only normal industries also. So
let's go take a closer look. Can we?
All the fuel bundles used in the past few years have found their resting place in this huge pool, more than 30 feet deep, filled with demineralized water. When a fuel bundle is removed, it emits heat and radiation. So to cool the bundle and shield the radiation, it is kept in this pool of water called the spent fuel storage bay. The minimum cooling period is 4 years, after which they may be sent for reprocessing.
This is the spent fuel receiving bay that I was telling you on the top. We have refueled one channel L11 today in the morning.
Okay.
So one of the spent fuel bundles of that channel is being discharged right now. So what you will see is the discharge of one of the spent fuel bundles, which has been refueled just about 2-3 hours back. So this, from this receiving bay, it will be going to the storage bay.
And the only thing protecting us is this, what we call the shield, is this water.
Shield. Water is shielding. It's a very good radiation shield, as well as it's taking out the decay heat from the fuel bundle. So it's also cooling the fuel bundle,
so
as well as shielding.
You maintain a water temperature also.
We maintain a water temperature and the water depth. Like here you can see it's around 5.5 meters. So this much is the depth of water. Yeah. And what we are seeing down below is, the water is that clear that we are able to see everything on the floor.
So a critical question. What are the chances of this water mixing with, say, groundwater or any other sort of water?
The chances are next to negligible. The system is designed in a way, this whole, like what you're seeing, there are the SS plates.
SS as in?
Stainless steel plates are there.
Okay, not Secret Service.
They're stainless steel 304 plates, and after, this whole pool is lined with these plates. And behind one layer, there's another layer of plates.
Okay.
And then there are other systems. This whole ground is also 5-meter waterproof. There's a waterproofing treatment also there.
And probably the most armored of vaults that you
it's
get.
most armored. There have been plenty of quality assurance checks we have done on this, including vacuum box testing, DPT and everything, so that there is no leak from the here. The spent fuel bundles will be coming out from this.
We will actually see the bundle.
Yeah, we will actually be seeing the bundles which we have refueled or discharged from the channels in the morning.
I never dreamt that I would actually witness this kind of a nuclear transfer happening with my naked eyes.
Those are the spent fuel bundles.
Oh. Once again, is it like a shell that I'm seeing, or is it actually the fuel that I'm seeing?
It's actually the fuel. Right now also you can see there is somewhat of a bluish tinge out there on the spent fuel bundles.
So it's not just that they are blue colored, it's a blue glow. It's like emitting light.
Yeah, it's called a Cherenkov light. This is a special peculiar characteristic of a spent fuel bundle. Actually, the speed of the radioactive particles in this water medium is more than the speed of light in this medium. Because of that bluish tinge is coming.
Oh.
And it was discovered by one scientist, Cherenkov, so it's said on this note.
So unlike a thermal power plant, where the coal cannot be reused, a nuclear power plant uses what is known as spent fuel. So when we see these uranium fuel rods that have been used coming here, they'll be stored in these cases, and eventually plutonium will be extracted from them, which can again be used as nuclear fuel.
India has a 3-stage nuclear program, which was envisioned by the father of the Indian nuclear program, Dr. Homi Bhabha. In stage 1, natural uranium is used as fuel to generate electricity. In addition, plutonium-239 gets generated. In stage 2, plutonium-239 with thorium will be used as fuel to generate electricity. In addition, U-233 will be generated. In stage 3, uranium-233 with thorium will be used as fuel to produce power, as well as more uranium-233. One of the key things about nuclear power generation is that the plant can be kept running continuously and power is produced without any interruption. To keep the plant running successfully, maintenance of the equipment is an integral part.
Nuclear energy and safety go hand in hand. Regular checks and maintenance are an integral part of the operations. Right now, I'm going to join a team that is getting ready for the action. Could you tell us what is happening in terms of maintenance today?
This is our fuel handling maintenance shop. If you really want to see us how we carry out the maintenance, then we have taken up one major maintenance job inside the reactor building. Unit 4. So if you would like to go, then I will take you there, but it's below the wall, below the reactor. And for that, we have to wear some protective clothing.
So that sounds
It's a
very
major
exciting.
job. Yeah.
Let's do that.
Okay.
This is a first for me. Now I really feel like I'm a part of a science fiction film.
Equipment reliability is one of the challenging jobs for the maintenance professional. If our equipment is safe, plant is safe, and plant is safe, whole nuclear society is safe.
It was a planned maintenance of the change of RAM assembly. It's the thing which is pushing the fuel bundles, which is taking out all the plugs. With this RAM assembly, we had completed 1200 refueling operations.
The RAM assembly is the heart of the robotic fueling machine. For servicing this part, the maintenance team needs to be in ventilated plastic suits and pressurized air masks to protect them.
That was an amazing experience. And the most fascinating part about this whole experience was that I'm at the cutting edge of technology, the very cutting edge. And yet, somebody has to do the nuts and bolts job with their hands. Now, these guys are the real superheroes here, even though I look like one, or dress like one.
But being dressed like a superhero still doesn't give me superpowers. So I still need to get my radiation levels checked.
Rajagopalan, I've just come from Zone 4. And could you tell me how would you measure my exposure to radioactivity if there was any?
Yeah. See, there are two personal monitors we are given to you. This is called TLD. This is the direct reading dosimeter. So you can see that while taking the emitter given you at 0, and now you can see the final reading is 2.335%. This is the dose you have received for today.
Micro
sievert, micro sievert. That is the dose you have received. But this is recorded here also. But similarly, every day you will be taking this when you take a job. You might have taken an RWP for working. And every day, this dose will be added in your TLD number in our software program. So end of the month, we will send this for reading. Whatever the dose registers, that is called the legal date.
What is the permissible limit?
We got two types of categories. One is the temporary workers and is the departmental workers. For departmental workers in a year, you can give up to 30 millisievert dose. But for temporary workers, it is 50 millisievert dose. That's the dose limit we are giving for that.
And how do you monitor the different zones? I noticed there are machines everywhere if you go from zone 4 to 1, lower zones.
Yeah, all these areas, all the zoning is based on our radiological probability of contamination. On that basis, we are divided. When you are exiting from each zone, you should check yourself you are not carrying any radiation with you. So that we call it as a contamination. That's why it is called interzonal monitors. It is mandatory that when you exit each zone, you have to thoroughly check for contamination. That's our zonal philosophy and the way we are controlled.
Based on the scientific data, there is no correlation between the radiation and the congenital anomaly. The second apprehension is that the radiation causes cancer. So if you see the data, cancer prevalence rate among the employees, those who are working in the close proximity of the radiation and the nearby, all samples if you take for the health assistant and based on the epidemiological survey, we have found that it is 1/5 when compared to any location where there is no nuclear power.
We are the graduate engineers. We can get job anywhere in the world. Still we are working here because we know the consequences of radiation are negligible.
If we take the entire our plant, average a person receiving dose from Tarapur P4, it's around 0.6 to 0.8 millisievert in a year. Even though your limit is around 20 millisievert or 30 millisievert. And Number of person exceeding more than 5 millisievert, if you say that it's hardly 1%. That's how we control. Even though we got the limit, we will not allow the person to receive that much. You got any praise?
So I hope it was a very clear-cut discussion and clear-cut information about the nuclear power station. So I hope you have taken down some notes from it, and also we have seen so many things from our discussion as well as these videos. So we will stop here for today, and then we will be taking this topic